Hello everyone, thanks for tuning in. This is the first episode of a new series that we are talking, that it's called Back to Basics. And in this series, we are going to be talking about all things technical about the acoustic of the acoustic guitar, on the design and evaluation and measurements. And in the latest periods, this topic, the technical approach to the acoustic guitar design and analysis, is getting a lot of interest. And this is a good thing because there are a lot of ways this can be profitable for both guitar makers in general and the industry. But we believe that some practices, some best practices can allow to profit the best, just to avoid too much fragmentation. And generally speaking, we think that in the information has to be correct. This is the starting point, of course, but it would be nice to be based on shared and validated research. As far as possible, links and bibliography of this series, as well as the others before that we already had here on the Loot groups, will be available in a dedicated section of the Loot group forum or on my website. So this is very important because this is something that allows everyone to evaluate and check for himself the information that is provided. And then information also has to be adapted to the situation. Of course, complication sometimes it's not the best way to get the results that we are looking for. And it doesn't have to be exclusive to be put in practice. It means that we are not suggesting to use expensive tools, of course, and tools that are simple to be adopted in a workshop on a daily routine for a guitar maker. And then, of course, useful. It seems maybe unnecessary to repeat this, but we don't just want to explore a technical approach just for the sake of being more wise or better than others. This type of analysis has to bring improvements, or in the quality of the instruments, or in the way we work on our instruments to, for example, gain some time during the building process. There are several possibilities that several ways a technical approach can bring benefits on our work. And these 3 points really are very important in order to build a solid foundation, a common ground, then after can be used for everyone to discuss, to exchange, if possible, to use the same software to exchange file or the same kind of format. In the future, there will be, if possible, some standard that will define with more details how measurement has to be performed. But for today, it is better to avoid fragmentation. This is the reason why we decided to go back to the basics. We want to put really some solid foundation to our approach to the acoustic guitar design and analysis. And today we are going to discuss theory and really to start looking at the main resonances of the acoustic guitar, how the acoustic guitar works, and what do we need to look as a starting point in an acoustic instrument for its evaluation. So I want this talk to be really an exchange. So as I told Ian, do not hesitate to interrupt, to intervene. I will go slowly. I don't have a lot of slides. I don't want to touch too many topics. I think it is better to really focus on the basis at the beginning and to discuss and to exchange. I would like to really to hear your opinion and to get in touch on all of this. So we can begin. The starting point is the interaction between the strings and the and the soundboard, of course. This is the basis of the way the acoustic guitar works. We all know that we supply energy to the strings, and the energy is then transferred to the soundboard via the saddle and then the bridge, and that the vibration of the soundboard generates sounds. This is perfect, but some more details about how the strings vibrate, how the waves are traveling within the strings and transferred on the bridge can be interesting in order to better understand how the instrument works and how can we also analyze and measure his behavior. So here we have a string, and this is taken from Alan Carruth's an article that is called String Theory, published in 2009. It's a very interesting article that you will find all over the web, and if you want, in my websites. So when we take the strings away from its resting position to pluck the string, we introduce a potential energy. Then there is a plucking moment. We leave the string, and in this moment, the start of the cycle, we see that the string is comprised in two segments, divided in two segments. So it is longer than the string in the resting point. So the tension has increased. Two waves begin to travel in the strings, one toward the nut and the other one toward the saddle of the string. And the travel of the strings continues. In the position B, we see that the string now is in three parts, but the angle is not changed a lot. And in the position C, in the moment C, a wave has arrived on the saddle or the nut. It doesn't matter for the moment. The other one is still here because we didn't pluck the string at the center. Usually we pluck the string on a quarter or closer to the bridge. And so the two waves doesn't arrive exactly at the same moment. But then again, at the moment D, the second wave has arrived and is bouncing back, because in this point here, string and the saddle, a lot of energy is transferred back on the string. Of course, not all the energy. Where we are on the saddle, energy is transferred to the soundboard. While usually on the nut, which is very rigid and heavier than the soundboard, most of the energy is transferred back on the string. Eventually in position E, the two waves are back together, and the point you can see here is in the opposite direction and place of the plucking moment. So this is how the physics of the waves traveling within the string works. And we can see that this produces two different forces on the saddle. And this is quite important to understand, because the first are longitudinal waves. And the longitudinal force has the same direction of the string and is created by the increase of tension that we have due to the fact that we are taking the strings, that we are plucking the strings. And so this is the force that is applied at the bridge, and it is usually orthogonal to the string. And we can see that this is the first moment of the force applied to the saddle, and in position E is the second moment. In this point here, the longitudinal tension is again at the maximum, and we have dissipated the kinetic energy, and now we have again potential energy, which is ready to come back and to continue oscillating on the string. Of course, the energy will gradually dissipate, and this is the decay of the note. But then there is a second force that is applied on the bridge, and it is transverse waves. In fact, this force is dictated by the angle that it is created here on the saddle and the changement of the angle here. So the higher the angle and the higher the tension of the string, the higher will be the transverse wave and the force that is applied on the bridge. So Alan Carruth measured these forces with using piezo. And here we can see that what it is interesting is that the point one is the longitudinal force. And we can see that its period is double compared to the transverse wave. This is because, in fact, here we see a semi-cycle. And we have the first impulse, the second impulse. While the transverse wave has just one changement from here. The moment where the string changes its angle and direction is the moment where we move from here to here in the force that is applied on the bridge. So, in fact, the longitudinal force has a double period than the fundamental. It means that if we are playing, for example, a sixth string, an E low, at 82.4 hertz, we will have a transverse force applied at the bridge at the same frequency. And longitudinal force at double the frequency, 165 hertz almost. So it will be an increase of the second harmonic. And also, what it is very interesting to note is that these two different forces act differently on the bridge, because the transverse wave, in fact, the transverse wave is applying direction, pumping the soundboard orthogonally in this direction, all over, turning like this on the string, while the longitudinal waves is rocking the bridge. Is the direction of the longitudinal wave is the same of the string. So the longitudinal force will pump the bridge and will excite mostly this type of movement of the bridge, while the transverse wave will pump the soundboard and will have the bridge rocking also. So it is two different phenomena that will increase different resonances of the soundboard at different frequencies. So the article by Alan Carruth is very interesting. So I suggest everyone that is into that wants to get with more depth into the knowledge of the relationships and interaction between strings and soundboard to download the article and to read it. And then the work of Trevor Gore also have been very interesting and useful to introduce more information about interaction of strings and soundboard to produce sound. Here, in fact, there are data that regards two different set of strings, steel strings and nylon strings. We can see that the energy, the force by the transverse wave, it's much higher than the force that is applied on the bridge with longitudinal waves. In fact, in the acoustic, in the steel string guitar, we have more than 8 Newton peak to peak. It's the third string that it is the highest tension, that it has usually the highest tension on the sets. And but in the steel string, longitudinal forces are still quite interesting in terms of level. while we see that on the classical guitars, longitudinal waves have the lower influence on the performances of on the instruments. We also see
Giuliano,
that, yeah,
can you explain that graph just a little bit? The EX, EY, AX. Is that important to know those, what those mean? Those are the individual strings?
yes, those are the individual strings, and we have the set of strings,
Okay,
and these are the transverse waves on the strings, and here it's a set on the longitudinal waves.
great.
The pluck amplitude is changing. When we change the pluck amplitude, of course, we change the force that it is supplied on the string. And also when we change the tension on the transverse wave, as we increase with the tension, we increase with the force that is applied on the bridge.
So these are Trevor's figures, Trevor Gore's
Yes.
figures?
Yes, this comes from Trevor Gore Contemporary Acoustic Design and Theory book.
What kind of rig did he have to measure the pluck amplitude?
It doesn't give details. I
Okay.
have the feelings that these are calculations.
Okay.
Because in fact, with some mathematics, you can calculate quite easily, in fact,
Okay.
these parameters. And what is also interesting to note is that if we think that, generally speaking, a steel string guitar has around 750 Newton of continuous tension of the strings, it's the tension that it is just necessary to keep the guitar in tune. The energy that is supplied while plucking the strings, at the maximum is at least 10 times lower. So it's interesting to note that most of the work that the structure of the acoustic guitar has to do is just to keep the instrument in place, intact. We know very well this, but it's interesting to have some number. We see that if we have at the maximum around 8 Newton of peak to peak for string, so that means that we can arrive around maybe 50, 45, 50 Newton of peak to peak transverse force plus 20 Newton of peak to peak longitudinal force. So it's 10 times lower than the actual static load that it is always on the guitar. So this is a starting point to understand that, in fact, the transmission of energy from the string to the body, to the soundboard and the body of the guitar is quite complex. We have different phenomena that produce different type of reaction on the soundboard at different frequencies. All of this is has to be taken care because, for example, if I play the fourth string around 180 hertz, which is the first, the second fret, I will have a fundamental close to what is usually the main resonance of the soundboard, and an harmonic that will also be reinforced by longitudinal waves at twice the frequency in a frequency range 360, where very often there is a long dipole on that guitar. So this can have a very strong effect, because shifting the long dipole from 360 to maybe 450 or 300 is not so difficult, and can really change the way we perceive mid-range on that guitar, just because we are considering the way the strings transfer energy to the soundboard in different directions.
Is it changing mid-range because are you trying to avoid a competition between frequencies, or like canceling each other out,
Because
or
if you have, because if you have the long dipole that is coincident with the longitudinal waves, it will increase the perceived loudness of that note. While if the long dipole, if that specific resonance is higher or lower, you will not have this kind of effect. So if you want to, it's interesting to put the long dipole in that region of frequencies. If you don't want, you move out. It is not so easy because changing the frequency of the dipoles is not really a joke, but it is something that have to be considered. Oh goodness, sorry. Sorry for the cough. In fact, this is not very basic, but this is something that it is not discussed very often. The article by Alan Carruth, where these images come from, is very interesting. And reading the article, there is not a lot of math. I will give you the link, Ian.
yeah,
To
we'll add it to the links in the
yes, yes, yes.
description of the video.
It is a free article available on the websites. So this is very interesting because then, anyway, energy is transferred to the soundboard. The soundboard is vibrating, and as it has a very large surface, if you compare the surface of the soundboard to the radiating surface of a string, you can understand that there is a very high difference. It's a huge difference on the radiation capability. I just wanted to show this animation because I think it's very interesting to understand how waves travels in the air. It is important to understand that the particles are vibrating around their position. So it's not the particle that there are moving. In fact, are moving from the source to our ear. Particles are really vibrating and are just transmitting energy to adjacent particles. And this creates a wave that is propagated in the air. So you can see clearly in this animation that the red line, the red vertical line, can be considered as a front of the wave, and it is traveling even if all the points, which are the particle of air, are staying around their position. It's the same thing that happens in the sea, for example. When you see that a boat is just moving up and down with a wave, it's not moving with the waves, just changing its position. And so the soundboard vibrates and generates sounds. But
That's a really powerful graphic. Is anybody unclear about what that graphic means? I just want to make sure that everybody understands what that is.
Yes, of course. And in fact, we can ask, we can stop a little moment. Do you want to go back to the string theory, or we can go on?
No, I think that's fine as long as everybody understands what that graphic means. I think I just wanted to, make sure everybody was clear on what that is, because that's really great. Yeah, feel free to move on. Nobody seems to be.
Yeah, this is very similar.
Andrew says is the particles bumping into each other what creates decay or loss of energy? I don't believe so.
Yeah. In fact, this is the damping.
Oh,
of course, the way the medium is made, the medium can be air or can be a solid, as for example, as a bell or a soundboard. And the physical details of the atomic structure and the bones of the material changes a lot the way particle interacts with each other, adjacent particle. And this is what we measure, for example, when we measure the damping of the tone wood. The way particle particles moves impact the damping and impact the speed of the sound within the medium, of course. This is the density and the stiffness, and all these parameters are connected all together.
Cool. Good question, Andy.
So this is the same with if we imagine a spherical sound source, which the acoustic guitar is not, because there is only one frequency where the acoustic guitar behaves like a pulsating sphere, and it's the monopole of the soundboard. The monopole of the soundboard is really radiated like a sphere this way. And this is also one of the reasons why it is the most important resonance of the acoustic guitar, because it emits a lot of energy in the room. But when we go to the guitar, we see that things are much more difficult, much more complicated. This is the frequency response, sorry, of an acoustic guitar, OM type. We have already been on this graph. And this is the starting point of the analysis of any acoustic guitar, the frequency response. And what it is strange is that instead of having a flat line, we have peaks and dips. And this is important to be really understood, because each resonance, each peak that we see in the frequency response is a resonance of the instrument. And when we are analyzing the behavior of an acoustic guitar, we have to look for the peak that corresponds to the resonance that we know have to be present in the instrument. We know that the first resonance have to be the resonance of the volume inside the box by the opening, the sound hole. We know that the second resonance has to be the monopole of the soundboard. And we already have to have an idea of what we will have on the screen before performing the measurement. This is very important. The measurement, we know how it is performed, but yeah, and I don't know if we will have the video on the screen, because no. So if I want to share everything on the
Oh
screen.
yeah, just share display instead of share the specific app.
Okay, share
I should
display.
bring it up.
Share the screen. Okay.
Share display.
So that should be okay. Oops. So the equipment that we need to measure the frequency response is very simple. We need a laptop with an FFT software. I suggest to use a Rumek Wizard, because this is a standard in the audio industry. We need a microphone, and this by Mini DSP, it's a USB microphone that is dedicated to acoustic measurement. So it is very convenient, because you don't need interfaces. You just connect directly the microphone to the laptop or the computer.
Are those
And
earplugs that you put in the strings?
yes, because I want to damp vibration of the strings while I perform the measurement.
Yeah.
Because I will be tapping the bridge. And those are earplugs, yes. You can also use the fingers to damp the resonances of the strings, but with the earplugs, it's more simple. And Rumek Wizard recognize the microphone, because they are designed to be working together. And you can load the calibration file. So in fact, the output, the acoustic output that you can see in the screen, it's calibrated. And then you use FFT from Rumek Wizard. We tap usually around the bridge, around the saddle, over the bridge. And the measurement is performed in a few seconds. And with Rumek Wizard, you can store it very simply. And it's the frequency response that you can see here on the screen. So it's very simple. It is absolutely non-destructive. I usually use a rubber hammer that it's not creating any type of problem. And and it is a repeatable measurement. So we already say that each peak is a resonance. So a little bit of understanding of resonance is requested, of course. This is a very simplified spring and mass resonance system. The mass is the inertial mass of the body that it is oscillating. And the stiffness is the spring constant, K. The equation is very simple, in fact. This is just telling us that the resonance frequency, the natural frequency that this system will resonate, is related to the compliance and the mass. The higher the mass, the lower the resonance frequency. The highest the stiffness, the highest will be the resonance frequency. It's very simple, really, as simple as that. And it is very also intuitive, if you want. It is clear that when you increase the mass, the sound goes down in frequency, the frequency, the resonant frequency. And as in the strings of the guitar, when you increase the tension, the stiffness, the tone goes high, goes up. So in this simplification, there is not the damping. It's not, we don't see the damping element. And of course, any type of resonance system has a damping, but for the moment, it is not necessary. What we need to do that each time that we think about a resonance, about a peak on the acoustic guitar, we have to imagine that there will be a mass that is vibrating and the stiffness that is connecting this mass to the ground on the system. So we just have to understand exactly what is the mass and what is the stiffness, and we will be able to master the resonance, increase or decrease its frequency, or change its behavior. Anyway, the parameters are just two: mass and stiffness.
Giuliano, can we just really quickly, can we talk about what M and K would be on the guitar? So just to clarify.
Of course. We go back to the frequency response that we see earlier. The first peak, it's always the air resonance. In this case, the mass, this is not simple to, it's not so very intuitive, but the way Helmholtz resonator works, the mass of the system is the part of the air that is in the sound hole. Yes,
the air column.
Yes, it's the plug of air that it's in the sound hole. So you can consider twice the thickness, 3 times the thickness of the soundboard, because there is an effect of prolongation. But you mean, I don't, usually it's 2.5, 3 millimeter of thickness. You can imagine that there is a disc of 6 millimeter of air on the sound hole, that is the mass. And this mass is bouncing on the stiffness of the air that is inside the box. Air inside the box becomes a spring, of course. As you know, on the syringe, when you close the hole, you cannot move the piston on the syringe because the air has a stiffness. And so if you increase or decrease the volume, you will increase or decrease the stiffness of the air inside, and you will change the resonance frequency of the air which is in the sound hole. Or if you change the dimension of the sound hole, if you increase, for example, its diameter, you will raise the resonance frequency. It will increase.
So is that what they call the Helmholtz resonance?
Exactly.
Okay.
Exactly. The first peak, it's always the air resonance. And in fact, if you close the sound hole, for example, with the rubber cover that are often used in live situation, and you take back the frequency response, this peak will disappear. Instead of having the peak, the curve will be going down from the second peak, and there will be nothing here. This is also why it is a very powerful way to reduce feedback, because if you close the hole, you lose that resonance, and the acoustic guitar will not resonate anymore at around 100 Hertz. And so all the frequency range in between 80, 150 to 100 Hertz, it will be much more solid to feedback issues and problems. The second peak, it's always the soundboard monopole. I have an animation for this also. This is a simulation of the soundboard of a Martin OM type guitar. On the simulation, there are not sides, there is no sides, there is no back, but the way the soundboard resonates is exactly the same. Of course, the boundaries of the soundboard are fixed, so it is as the soundboard glued on fixed edges. And we see that all of the central part of the soundboard is moving up and down like a piston. This is why this is called monopole, because in fact there is only one pole that is moving up and down. And it is very interesting to note that the center of the monopole is always the bridge, because the bridge constitute the bridge with the saddle and with the strings and the end balls of the strings usually constitute 50% of the mass of the soundboard monopole. And so it brings with him the center of this resonance. And everything else which is outside this light blue ring here simply does not participate to the soundboard emission. So all of the rest, all of this blue part of the soundboard are just not vibrating. And this is also quite important because we need to understand that even if we increase a lot the dimensions of the soundboard, it doesn't mean automatically that we will have more soundboard vibrating. Because in fact, we have a limited quantity of energy that is coming from the strings. And this will be the main factor. This will be the parameter that will really change how big part of surface of the soundboard will be radiating acoustic energy. If we want to increase acoustic energy, we can reduce the weight of the soundboard, because of course, this is one of the most important parameters. In this case, Ian, the mass is everything that it is inside the light blue ring. You can see clearly, you know, the red part and the green part, the yellow part. Yeah. All of this is the zone of the soundboard that it's the mass of this resonator system. So it's not the whole soundboard, it's just that part of the soundboard. It's very important. If we measure the complete mass of the soundboard, we might find that it's around 100, 120 grams. If we calculate instead the mass of the monopole, and we can do it. In this type of guitar, it is usually around 75 grams, 75, 80 grams, the Martin OM guitar. And the stiffness of this resonance system is the combined stiffness, of course, of the bridge, of the soundboard, and of the bracing system. The bracing system is supplying a high percentage of stiffness. We can estimate from 50 to 70% of the stiffness coming from the bracing, because bracing is very high, in fact. And they have a very, very strong influence on the stiffness. This is also why, by shaping a little bit the scalloping of the X on the Martin type bracing, we can change a lot the resonance frequency. And of course, yeah, if we reduce the height of the brace, the soundboard will be less stiff and the resonance frequency will drop. We can arrive to drop 5 to 10 hertz easily by shaving the braces. Of course, we have to pay attention because we always have those 75 kilogram of static load that will belly the soundboard. And so it is always a question of compromise and bracing design to obtain an instrument that have to be, of course, reliable, but also responsive.
Question from Rosella. In two identical steel string guitars that only differ by having a 12th fret neck joint and a 14th fret neck joint, hence the position of the bridge is different, will the center of the main monopole also be positioned in two different points? In other words, does the bridge move the center of the main monopole if glued in a different position? I would think, because the bridge counts as part of your mass. Is that right? Am I getting
Yes.
that right?
Of course, it is exactly like this. In fact, in my design, for example, I put the neck at the 13th fret, and this is putting the bridge exactly on the center here. If you see from far away, this is really the point where we close a theoretical circle. And yes, the bridge brings with him the center of the monopole. If we shift the neck at the 14th fret, and with him, of course, the bridge, we will have a zone here where that blue part increase. We will have more distance between the edge of the lower bout and the active part and the active zone of the monopole. This is something that is very clear in, of course, guitars that has the fret, the neck at the 14th fret. But and it also depends on the shape of the body, of course. But the answer is yes, of course. At the same time, sometimes I imagine that there is something that it is researched by the guitar designer, or that creates a sound that it's interesting, because one also has to pay attention not to have too much low frequencies. Sometimes if the soundboard monopole is very low on the soundboard, it can really create a prominence of the monopole on the frequency response, and the sound with mid-range that can be muffled, that can be a little bit in second plane. So it is always a question of compromise. So sometimes also the back can be present in the frequency response. The monopole of the back is very similar to the monopole of the soundboard, but in different type of bracing, it is possible that instead of having one clear monopole, we will have a different part of the back resonating at different frequencies. Also because on the back there is no bridge, so the moving mass of the back it's lower than the moving mass of the soundboard. There is not a center of gravity for the distribution of the mass, and so with the traditional type of bracing, Martin bracing, we have 4 ladder bracing that are very strong, 20 millimeter of width by 10 millimeter of 8. And this produces a back that has a very high resonance frequency and it is not active. If we want to if we want to activate the back, we have to pay attention that we will activate only a part of the back, usually it is the lower part, by using a very strong bracing on the higher part of the back surface. And we have to really take care because activating the back means that we are using energy from the soundboard.
I was going to
So
say what like on the soundboard we know that the strings are what's driving the soundboard, but what's driving the back and
it's the soundboard. In fact,
Okay.
the back and the soundbar are coupled because they share the same volume inside the box. And so the soundbar vibrates the air inside the volume, and this vibration excites in resonance the back if the resonance frequency of the back is close enough. Because if you go too high, you see, you always have your peak of energy. If you are in this zone close to the center of the peak, 4 semitones, higher or lower, usually it is higher, you still have energy which is useful to activate the back. If you go too far away, 300, 350 hertz of resonance for the monopole of the back, there will be anything. The back will be dead because there won't be enough energy transmitted from the monopole of the soundboard. But when we take a frequency response, we should always look if there is something close to the main monopole, and this could be the back. It's simple to check if it's the back. You just have to put the microphone close and you tap with your rubber hammer directly on the center of the lower bout with the microphone close to the back, and you will see evidence of its resonance frequency. So if it's here, you see that it will be here. Otherwise, it will be, usually it is higher.
Does the back wind up dampening the top when
Yes.
you activate? Okay.
Yes, of course. This is why care has to be taken. With a mahogany back, for example, which is very light and very active, very mobile, if you want, the risk is that you take a lot of energy from the monopole, and the peak of the monopole will lower. You will have almost a peak of the almost same height coming from the back, but you lose projection because, in fact, the monopole is projecting sound. Energy that is activating the soundboard is energy that it is taken and from the resonance of the monopole of the soundboard. So it's a question of compromise. For example,
Oh, I was just going to ask, what do you get in return for activating the back if you're taking that energy from the top?
What you have in return is that you can have a very, very light soundboard which has a very high peak of energy on the monopole, maybe too high. When the soundboard is too light, it can become a problem. It can activate a lot of wolf tones. It can be an aggressive sound. So you can design a very light soundboard and then put a back close to the soundboard that take away a little bit of energy because it's too much. You take away a little bit, you put 40 hertz higher, and you are amplifying a wider range of frequency. You have a sound that is richer. But you have to be careful, because if the soundboard is not very live and you have an active back, the risk is that the soundboard becomes almost dead. And this is and yes, maybe you will have more richness of sound, because if you spread more resonances, the sound is richer, generally speaking, but you will have less projection. So, for example, classical guitar, concert classical guitar, they are always built with a dead back. In general, classical guitar, they have a dead back, because classical guitar, you have lower energy from the strings, and you want to put all that energy on the monopole. And because in classical guitar, you have other resonances, such as the long dipole, for example, which very often can be close to the monopole and take the place of the active back. And then in a concert guitar, you use a lattice bracing, because the monopole is projecting a lot energy in the room. So in the concert room, you have a lot of projection. So you don't want to have an active back for a concert instrument. But for finger playing, if you want to play the instrument in your couch, or for your friends, for if you like to sing, if you're a songwriter and you look for a rich timbre, it can be an interesting solution. In any case, in doubt, it is better to have a passive back. In any case. And then on the frequency response, you look for other resonances of the soundboard. And here we have the long dipole and the cross dipole. I can show you how these resonances look like. When we talk about dipole, we have two poles. That's not this one. Oops. Yes, it is repeats. So we have two poles that are in opposition of phase. And very often in the long dipole, the bridge is exactly on the center between the two poles. And in the cross dipole, the direction of the center is usually vertical, and this is why it is called cross dipole. And in this case, the bridge is rocking. And this type of resonance is excited mostly by transverse waves on the strings. While this type of resonance, usually the long dipole, is excited by longitudinal waves, because as we have seen, the longitudinal waves tilt the bridge this way and excite this type of resonance, which is very often found in classical guitars, more than in acoustic guitars. It is interesting to understand also how standing waves works. This is another animation here that is showing you what it is as standing waves. The standing wave is the red wave.
Oh, 1 second. We're not seeing the animation.
Are you not seeing?
No, I think you might have try sharing. There we go.
A standing wave is the red wave. It seems that the wave is standing. It's just going up and down. But in fact, the standing wave is the result of two different waves that travels in opposite direction, that bounce back and forth on the soundboard.
So
And
the red wave is being generated. It's by the vibration of the green and the blue.
interaction of two waves that travel in the soundboard. In fact, the waves travel. When you put energy in the soundboard, energy is traveling through the soundboard, arriving at the edge. A part of energy is dissipated on the sides, but a lot of energy bounces back and continues to bounce within the soundboard as the decay of the note goes down with the damping. Eventually, it will be completely absorbed. But for a certain period of time, you will see this bouncing on the soundboard that apparently from outside is just this movement. But in reality, it's the waves that are moving inside and that are interfering at sometimes zero, sometimes maximum output. So this is an animation that very clearly shows what it is happening. And what happens within the soundboard with all of the soundboard modes is exactly this. At different frequencies, we have different resonance phenomena. And here we can see the most important. At low frequency, the monopole. Then we have the long dipole, the cross dipole, the long tripole, which is the same, but we have 3 poles, and the cross tripole. So we have to be hunting for these modes on the frequency response. We have to know that each and every acoustic guitar has at least this 6 mode, very clear. And when we take a frequency response, we have to look for this. If we don't do this, we are not getting interesting information. Sometimes it is difficult to find this mode because, for example, when the soundboard is very heavy, there are not a lot of higher order modes, and the tripole will not be very evident. If the bracing is a lattice, for example, lattice bracing, this type of bracing is concentrating a lot of energy only on the monopole, and we won't see a lot of other higher peaks. Of course, when on the frequency response, we don't have all of these peaks, we know that the soundboard is not very alive. It's not very alive at higher frequencies. But sometimes this also happens because there is a lot of energy that is concentrated on the first peak. So this is why we need to be looking for this. And the starting point for the evaluation of an acoustic guitar, together with the frequency response, is identifying all these modes of resonance. The first mode, it's always there. The soundboard monopole is always there. Is there an active back? What about dipoles and tripoles? Do I see peaks or the curve is going down? This is the starting point of a guitar analysis, because then when we know the frequencies of the main modes, of the main resonance mode, we can put these frequencies in our table, and we can start to understand what are the performances of the instrument that we are analyzing. We know that in classical guitar, Helmholtz resonance is in this frequency range, between 90 and 110. In acoustic guitars, between 80 and 110. In archtop, between 100 and 150. So is the guitar that we are, for example, an acoustic guitar, are we at 110 or are we at 90? Because a guitar that has a first peak at 90 Hertz has a very powerful low output. If it is at 110 or maybe higher, it means that it's a small guitar or it is a very dynamic instrument. It means that if it's not producing a lot of low frequency, at least it has to produce a lot of mid-range. So it will be maybe more bluesy, a blues box, for example. In an archtop guitar, we don't have a lot of low frequency. Usually the first mode is around at 140 Hertz. Then there is a soundboard monopole. It's the highest peak, and it is the resonance that it is producing most of the sound radiated by the guitar. So it's very important. Again, where is the balance of the instrument? In classical guitars, in between 190 and 220. In acoustic, 160 to 100. In archtop guitar, again, 200, 250, much higher. Archtop guitars usually have everything moved upward. And this is why they project a lot, because there is not a lot of low frequency, but there is a lot of projection. So the guitar can cut through, for example, an orchestra, or in the mix, it goes very easily through the mix. And then, so what we were talking about, dipoles and tripoles. Are they evident or not? Because sometimes these peaks are really not there. And it doesn't mean that the guitar is not a good guitar, because maybe we are looking for a guitar that has a very tight sound and a very nice projection. So in this case, the soundboard will have a bracing that it's different and will concentrate more energy on the monopole. Or maybe the soundboard is very heavy. Sometimes it is like this, but also when the soundboard is very heavy, the guitar can be interesting because it means that it is not sensitive to wolf tone, and generally speaking, the sound is very even. When you play over the fretboard, you don't have very big differences. I was looking for, sorry, another. Do we have questions, Ian? Do someone wants to ask some questions or curiosity?
I have a couple, but I think I'll let everybody else kind of have the floor first. And they're more curiosity questions than directly related to what we're doing. Does anybody have any questions? James Rodman, you look engaged.
No, I don't have any questions.
Okay.
I'll have a go.
Yep.
So you were saying about choosing as to whether to have a guitar that has the more tripoles, more dipoles, and less, more or less, and more of the monopole. What are you doing to the bracing or the top to achieve those things? I know there's probably a million and one different ways to do it, but like, are there any kind of basics that you can kind of look at and shoot for?
There are mainly two parameters that affect the presence of higher order modes. I mean, the resonance is always there, always, because it's a physics, it's just physics. You will always have the table always divide in the same way. There will always be a monopole, a cross dipole, a long dipole, a cross tripole, a long tripole, and then it will be four poles and others. The thing is that maybe you are not able to see those resonances because they are masked. Because one, the mask can be too high to have evidence of higher modes. And when the mass of the soundboard is very high, in fact, there is not a lot of energy which is activated at higher frequency, and the higher order modes are masked. Lower amplitude. This is one parameter. But if the soundboard is and bridge are light enough, then it's the bracing system. And the theory and the practice also tells us that a bracing system that has interlacing all over the soundboard, such as lattice. Lattice is X's bracing, and in classical guitar, it's really the whole soundboard that is covered by lattice bracing on the back. This type of bracing makes the soundboard a whole, in fact, and it is the bracing that it is more facilitating monopole and is more masking higher order modes. While, for example, the typical Martin X bracing with the two lower tone bars, the lower bout of the soundboard is decorrelated, if you want, because the two tone bars, in fact, if this is the X, the two tone bars here leave these parts free to move, and this part of the soundboard can facilitate the two dipoles and tripoles also. While if you have a tripole bracing with a typical X or double X on the back, this is also the type of bracing that is not facilitating higher order modes, dipoles and tripoles, but mostly concentrating energy on the monopole. Keeping in mind that it's a different timbre than it's a sonical balance that we get. It's not about being better or worse. When you put more energy into the monopole, and if you have the same mass of the monopole and of the soundboard, you will have more projection and you will have a lot of dynamic. And very often that dynamic can really be very interesting for the player, because it is something that it is perceived very clearly when you play. While if you have a lot of harmonics at high frequency, the sound can be a little bit more sometimes off focus. So it's always a question of balance.
Sorry, I got him. Larry Atha wants to know, did that get you, Andy?
Yeah, it's definitely got me thinking.
Okay. Larry Atha wants to know,
Absolutely.
what do you think happens when the Gounod Wagner type double top classical guitars with those guitars? Have you tested these? What is the effect of constrained damping layer from the Nomex and epoxy layers? Does it shape the higher frequencies significantly? For instance, does it act like a filter? In Frank Moon's chaotic vibration book, a constrained damping layer could result in chaotic modes. Any of that reach out to you?
I don't have extensive experience in this kind of design. I had the chance to measure a pair of instruments with a double top, and it seems to me that it's a type of construction that it is facilitating the monopole more than other type of higher mode resonances. I didn't see any kind of chaotic behavior, but I have to say I don't feel really experienced enough to express an opinion. I am sorry. I think it is very complicated, but for the moment, I cannot tell more. I cannot tell you more than this. It will be interesting, of course, to have a more in-depth analysis, maybe a couple of instruments.
Okay.
To begin with.
Rosella wanted you to repeat the part about harmonics. Can you be a little bit more specific on that, Rosella? I'm sorry. Or if you want to just repeat what you said about harmonics when you were answering Andy's question.
Harmonics are, in fact, higher order modes. Yes, it's not maybe 100% correct, but yeah, I was referring to higher order modes. This is what very often musicians call overtones. The dipoles the tripoles and the other modes that are higher than the monopole, of course. And yes, it was in reply to Handy, how to facilitate the production of these modes. And yes, it is a bracing system. It's a bracing design that disconnect part of the soundboard. Keeping in mind that that the bracing, the table always have tendency to produce similar resonance mode. You will always have a dipole, a long and cross dipole. You will always have a tripole. And if you want to change the shape of the modes, you really have to design a very accentuated bracing system, such as, for example, the Martin design that has the two asymmetric tone bars that are completely asymmetric and takes all the lower bout. Otherwise, you will have very small differences, generally speaking. There was a period where we used to think that the higher part of the bridge, where the sixth string is connected, is more related to low frequencies, and the lower part of the bridge is more to high frequencies, and that just changing the shape of the bridge or putting a little bit more mass in or there, we're changing the way high frequencies and low frequencies goes on travel on the soundboard. It is not just like this. It's just not like this. You always have to think about this image here and the fact that there is always a monopole, that of course can be slightly asymmetric if the bridge is hugely asymmetric here. If, for example, there is a missing shoulder, some guitar design here have a part of the binding removed to have an armrest, no? And this, of course, is affecting the how the monopole is on the soundboard, and the symmetricity. How do you say, Ian? How it is?
Symmetrical it is. Yeah, that's fine.
Yes. But there will always be a monopole here, and there will always be a dipole here, and a tripole. So you can change slightly those figures, but don't imagine to be able to completely change the way it behaves. Also, because why would you want to do something like this? It's also important to have clear ideas, and this is the idea of having a foundation. It's here. The foundation is starting always from the frequency response, looking always for the main resonances, keeping always in mind that a resonance is here. It's a mass and a spring. What is the mass? What is the spring? How the position of the frequencies and how amplitude of the resonance frequency is changing the sound of the guitar. Do I have problem with Wolf tones? Do I like the sound of the instruments? What do I want to change? Of course. This is the starting point of the analysis.
I was going to ask if nobody else has got anything. What do you think about any of those old, back around the turn of the century, you saw a lot of instrument designers messing with the air chamber, like the one that comes to mind is like the McAfee kind of baffle system that was on the inside of the guitars. Do any of those, you don't see them around much anymore. Does any of that messing with the air column on the inside of the guitar, does any of that stuff make sense anymore? Or has that just gone away completely?
Frankly speaking, Ian, I am not very familiar with those
okay.
kind of things. very often what I saw is very often practices intended to change the behavior of the first mode of resonance of the inside the box. I would need to have more information about to be able to answer you correctly.
Okay.
I'm sorry.
I'll send you some pictures and we can talk about it some
Yeah.
other time, but
Yeah.
yeah, cool. Let me
Okay,
make sure
so
we're not-
So I would say that what I wanted to do, Ian, for the next episode is to play around a little bit with measurement of the frequency response, because measuring the frequency response pose some I don't want to say problems, but we have to take care of several parameters during the measurement. So it would be interesting to have a really a workshop, an hands-on for the measurement of the frequency response, maybe with different instruments, maybe with some builder or a friend that's lend himself to play with us.
Okay. Let me know what you need. We can certainly work that out. So we would need to have multiple people with the software and the microphone and the mallet. Is that correct?
Yes, multiple people or someone with several different instruments.
Okay.
The idea is to make a measurement, analyze the instrument, have a look at strange behavior, strange things, and run diagnostic.
Let's reach out to the group and see if we can find somebody that we can do that.
Yes, Lariata to everyone. Yes, the Tornavots. It's just a duct that is inside the body that changes the height of the column of air that it's in the opening. Of course, if you put a cylinder on the back, you are lowering the resonance frequency because the column of air becomes higher, and so the mass, and this shift the resonance frequency down. That is the Tornavots, of course, but you are not talking about Tornavots, right?
No, I was talking about stuff like that.
Yes,
if
plates, resonance plates, yes.
Yeah.
I have some feelings, but yeah, I don't remember exactly. Anyway, a lot of tests has been made on the acoustic guitar over the decades, I would say
centuries. Yeah.
It's an incredible instrument.
Absolutely. Do you think historically speaking, just out of curiosity, like how were I mean, we've got these great microphones and the computers. How were the old timers doing it before microphones and before resonant testing? Were they just listening? Were they just doing it with ears?
What I think old timer were using, it's they had, of course, access to a resonator that were used to tune instruments. If you think about Helmholtz was analyzing a timbre of an instrument with his resonator tuned to different frequencies. And as we have a tuner at 441 hertz, you can have the same tool tuned to, for example, all of the notes on tempered scale if you want, and you can use that tool to tune with a high precision a resonance of the instrument. I have the feeling that this was used. Sorry, it's not just a feeling. Trevor Gore in his book is talking about it. He measured a lot of classical guitar from historical builders, especially Fleta and others, and he saw patterns on the tuning on the instruments with very high precision, such as very fragments of hertz. So in his analysis, his thinking is that, in fact, these guys knew very well what they were doing. They had tools to tune the instruments, and they had also knowledge about main resonances and main parameters. If you think about evolution of the classical guitar from Torres to Fleta, for example, they were doing things that made a lot of sense. My feeling is that that was the golden age, and that after the industrial period, now we are struggling to come back to a very high level of knowledge. Even if we have incredible tools, we are building with a lot of magic. We have incredible experience because, of course, today we have a knowledge that is really built over, as we say, decades of experience. But we can increase, we can improve the way we use these tools. I think I have this feeling, and this is changing. This is changing a lot.
Rosella indicated that plenty of measurements to share with at the next meeting. That would be great. I'd really like to see that. Everybody who's
Yes.
measuring to share measurements and talk about
I
measurements.
think that a common session of measurement would be really interesting.
Yeah. I did want to ask you, when you're testing the resonance of the guitar and you hold it by the neck, does placement of your hand on the neck anywhere affect at all the resonance, do you think, or is it so minutely that it's not worth talking about?
Sorry. Yes, it affects a little bit, not the resonance frequencies, because the resonance frequency doesn't change. The frequency is there, but the relative amplitude, it can change a little bit.
Oh, okay, yeah.
Because in fact, when I was talking about standards are important because they tell you how you have to measure something. Really, the best way, the best way, I don't know if it's the best way, but it's most consistent way to measure a frequency response is like this. Because the body is resting on my leg in this point where I am really not affecting a lot the resonances of the body. The neck is untouched, and I can also hold it here. I can put my microphone, just 1 moment. I can put my microphone here. I use the hammer. So this way, the neck is really not affecting, because the thing is that the first resonance that the guitar has, it's called the body resonance, in fact. And this resonance has 2 points of null here and here, and the whole body is resonating like this. It's very simple. It's very clear to be heard. If you take the guitar here, just and the first fret, and you tap here. I don't know if I guess that you cannot.
Yeah,
hear
it's gonna take it.
The whole guitar vibrates. If I take the guitar here and I tap here, nothing is happening.
Yeah.
Because in fact, there is this resonance here that can be affected when I take the guitar like this.
Yeah.
It can change a little bit. It depends on the stiffness of the neck, of the stiffness of this joint, and yes,
Is it kind of like just grabbing the note on a piece of wood when you're tap tuning or tapping a piece of wood?
Exactly.
Cool.
So yes, it is affecting the results. Of course, for quality control purposes, you would need to design a rig that it is very, very consistent.
Yeah.
If you want to compare it with a higher precision, 2 different instruments. And so maybe designing a rig to hold the guitar. Doug Proper would be very happy with it, of course.
Yes. Well, I like the playing position standard. I think that looks for
The thing is that when you hold the guitar in your hand, you have more freedom to tap in different points. And this is it gives you more creativity. A list of guitar that have been measured to see the difference.
well, you have a ton of measurements.
Yes, I do. There is already a file that it is shared on the design and testing forum on the Loot group. And the idea is there also to share different performances of different instruments.
We can, I'll share it again with this one. I'll dig it up and tack it onto this one too, just so that it's fresh.
Then again, Lariat,
Andy said he'll find it.
Daniel Frederick that made static measurement for stiffness. Yes, of course, it is feasible. I mean, static measurement for something that will be vibrating is not the best. It is more interesting to have dynamic measurements. The static measurement is a measurement that you perform by putting a weight on a plate and measurement the displacement. But this is static, of course, so you don't have any viscoelastic properties activated. So it is more interesting to have the wood vibrating. And to have the wood vibrating, you use a hammer, or you use, as in the jig here, you can use a marble that goes down on a sample of wood to excite the wood in vibration.
Has anybody done a so the simulation that you show is of, you know, the resonance. Has anybody done a simulation with a string going to the bridge and actually getting the different resonances of the string acting on the top as well?
Not to my knowledge.
Okay.
Also because why doing so? I mean, it is working on a virtual model of something that exists. It's a very delicate job. And already have a meaningful simulation of just the soundboard is not simple.
Yeah.
In that simulation, for example, I have wait. I have a force that is applied on the saddle, orthogonally on the saddle, and I am considering the whole saddle as a contact point where I apply my force. But if I want to simulate the way the saddle would react to a longitudinal force, for example, the pull of the string for a roll movement, yes, I can do, but
did you make these
delicate.
simulations, Giuliano?
Huh?
Are you responsible for making these
Yes,
simulations?
yes,
Oh wow. Oh wow. I didn't know that. That's great. Yeah, no, I was just
yes, these are simulations that I made for a paper that we published in 2021 with a friend of mine in UK. But yes, this is a tool that is very used for audio simulations. But usually you try to simplify the model. Usually you try to ask yourself one simple question and you look for one simple answer, one at a time, because the more parameters that you put together, the more it becomes difficult to have something meaningful. So what are you looking for here? Is what do I need in my model? And usually you try to make it simple. So simulate the way you play an entire guitar, maybe some Japanese guy at Yamaha. But then again, what they are doing with it, because I know that the guy in Yamaha are doing incredibly advanced simulations, and they like to do it. Japanese aces in this type of approach to the industrial design. But then, what do you do with it? This is the thing.
You make Yamahas. All right. Let's see here. All right. Should we stop there, you think? Or seems like a good stopping place. Do you want to keep going? Do you have more?
No, for me, it can be okay like this. I will. I think that's.
I think that was awesome.
Yeah,
I have a
for
quick
the-
question.
Yeah.
Yeah.
Sorry I was late. I had some family stuff. I was just curious, when you build your guitars, are you using a dead back or a live active back?
It depends.
Okay.
This one has an active back,
Mm-hmm.
because it's a steel string, and I have a very light soundboard with a very heavy back. So the mobility of the back is not very high. It's ebony. So it's just it adjusts a little bit without without absorbing too much of energy from the soundboard. But for example, in another model that I am making, which is a nylon string guitar, I am not using an active back because I don't need it, and I prefer to concentrate all the energy in specific frequency. And also, I have other resonances of the soundboard that are very close. The cross dipole, it's in my say chord, the cross dipole is at 260 hertz with a monopole at 190. So it's already very close, and there is not space to put another resonances in between. It's not useful. So I think that sometimes it can be for in certain specific type a little bit. Sometimes you don't need it.
So you're not one way or the other, like
No,
you
no,
use
no.
both. That's really cool. Thank you.
I mean, yeah, thanks to you. Generally speaking, I think that most of the technical solutions that we know today have their meanings and have their place to be. Thing is that you just have to know what you're looking for and being able to choose and also of course to realize, of course. So adapt also to the wood that you're using, because using different wood requires different kind of technique. Mahogany is has half the density of ebony, so it is more mobile, it is more prone to be excited in resonance, and you have to take care of this.
Makes
That's
sense.
just an example.
Dave, was there much of this going on at Taylor when you were there? Was there resonance testing?
Yes and no, but not really. The most testing that I saw done was when they created the first expression system, and we ran guitars through the laser interferometer, where you could see the top and the sides and the neck all undulating. But they were looking for where to put their sensors that they had developed, not to improve the sound of the guitar. I think Bob just got lucky. They didn't even try to tune a guitar until like in the 80s, tune a top. Dan Crary wanted a dreadnought that was really powerful, and that's the first time they actually made an effort to shape a sound.
Yeah.
And my work with Andy, he was I would ask him how the guitar was functioning, and he would just repeatedly tell me what Young's modulus theory was and didn't let go any of the. But he did say that the V-brace is just a super powerful monopole. That's where it gets the most sound.
Cool. Let's see here. Andy said, so with a small guitar, am I right in thinking deadening the back will give me the best chance for volume and projection? And you do that by increasing the frequency outside of etc. 300-ish hertz range. I'm not sure what that means, but I'm gonna say yes. Yeah, let's leave it there. Let's get Andy, get that guitar done, and we'll in the next session we'll tap on it. We'll test it. Get that microphone. You gotta have one of those microphones around.
Yep. I mean, in a small guitar, usually you already have a powerful monopole because in a small guitar you have a small soundboard. So the monopole usually it is very active. It's light. It's lighter than a dreadnought. So I don't know. More than dimension, for me, it's important to choose the type of sound that you are looking for. That it's really the character of the instrument that it's defining the choices that you more than its dimension for me. Of course, a small guitar will always be different than a big guitar. This is yeah.
Cool. All right. Well, let's leave it there. Everybody unmute and thank you. Thank Giuliano for taking the time once again to really like bring the fire to the humans on this
Thank you,
endeavor.
Giuliano.
Thank you.
Dan.
Thank you.
Thank you.
Thank
And
you.
Thank
I'm
you.
really looking forward to comparative analysis here. Like I think that's going to be a lot of fun. So
Yes, we have to work on a nice organization for that.
yeah, I wonder how best to do that with everybody's computers. Are you envisioning it? I'm going to stop recording now. Hold on.